Okay, so what about lone pairs? Because some molecules have a lone pair in the central atom, or maybe 2 or 3. Electron geometry is where we look at the electron groups and determine how those spread apart. Molecular geometry is the arrangement of the atoms. If there aren't any lone pairs on the central atom, then the electron and molecular geometries are going to be exactly the same. The difference comes when you have a lone pair. So let's look at ammonia. Always helpful to have the Lewis structure. I'll write it down here. So the Lewis structure for ammonia looks like this. Here's the nitrogen. There are 3 single bonds and a lone pair. How many groups is that? That's 4 groups. What do 4 groups do? They make a tetrahedron, right? So here's the electron geometry looking at the electron groups. They're making a tetrahedron. The molecular geometry just looks at the atoms. Because really, how big is this lone pair of electrons compared to an atom? Really tiny, right? In terms of its mass, very, very small. So the way I think of this is, you look at the electron groups, and those are the balloons. That's the electron geometry. Then if you have any lone pairs, pretend that that balloon is invisible. It's not that you're going to pop it and get rid of it, because that would change how the other balloons arrange themselves. It's invisible. So if this is invisible, what are we left with? We're left with this shape, right? Well, this is a triangular pyramid. It's got a triangle at the bottom, and it rises up to a point. That's called a trigonal pyramid. It's not trigonal planar, because trigonal planar would be flat. This guy poked down in the middle, be flat in a plane. Here it's poking up. And the reason it's not flat is because of that lone pair. That lone pair is repulsive and causes these hydrogen atoms to be a little closer together than they would if it wasn't there. Any questions? The lone pairs are actually more repulsive than the bonding pairs. And the reason for that is, here we have a bonding electron pair. It is stuck between the nuclei of the 2 atoms it's bonding. And so this is how much space it can take up. This lone pair is actually taking up more space because it's tied to this nucleus, but there's nothing constraining it on the other side. So it's bigger and more repulsive, and yet it's just 2 electrons. And so in terms of mass, it has basically no mass. These are atoms, they have protons in their nuclei, and so those are more substantial. So the molecular geometry looks only at the atoms, but the electron geometry has to consider the lone pairs as well. So this is more repulsive. So here, if we had a perfect tetrahedron, the angles would be 109.5. But because this is a lone pair, the hydrogen atoms are like, ew, gross. I'd rather be close to these other hydrogen atoms than to that guy. He's nasty, right? Repulsive. So these will squeeze together a little bit. Instead of 109.5, for ammonia it's 107. It's a little less. And then if you were to measure the angle between the lone pair and the hydrogens, it would be greater than 109.5. Again, I don't expect you to remember 107, but you should be able to tell me that it's less than 109.5. Any questions? Let's look at water. So here's the Lewis structure for water. We look at the central atom. How many electron groups? 4. 2 lone pairs and 2 bonds. What do 4 groups do? They make a tetrahedron. So here's the tetrahedron. We have a lone pair at 2 of the positions and bonding pairs with hydrogen atoms at 2 of the positions. That's the electron geometry. To look at the molecular geometry, we make the lone pairs invisible. They're invisible. They're there, but they're invisible. Do you ever feel invisible in a crowd sometimes? Like, there's all these people doing stuff, but nobody's talking to me. That's how the lone pairs feel. They're alone. So we've got this shape. They got super creative with that name. It's bent. It's not a straight line, it's just bent. Sometimes you see a book called angular, but we're just going to stick with bent. It's a nice short word. When we look at the Lewis structure for water, we're tempted to think that it's linear, right? Well, why not? We'll just put those lone pairs on opposite sides and the hydrogens on opposite sides. But this is thinking 2-dimensionally. A screen or a piece of paper. It's not constrained to that. It can pop into 3 dimensions. And so those 4 groups will make a tetrahedron. So it makes a tetrahedron, but the molecular geometry is bent. And again, those lone pairs are more repulsive, so we would predict that the bond angle between the hydrogens is less than 109.5. It's been measured, and it's actually 104.5. So yes, it's less. Any questions? These are squeezed together more than the hydrogens in ammonia because there are 2 lone pairs repelling. So the relative repulsion of electron groups, if you have two lone pairs next to each other, that's the most repulsive situation. A lone pair with a bonding pair is intermediate, and 2 bonding pairs are the least repulsive. So here in water, this is a bonding pair and a bonding pair. And so the repulsion there is less than from the lone pairs that are also on that molecule. So we see the bond angle here with no lone pairs, 109.5, 1 lone pair, 107, 2 lone pairs, 104.5. The more lone pairs, the closer together those atoms end up being. Well, what if we have 5 electron groups and some lone pairs? So SF4. And again, it's important to have the Lewis structures. So we've got 4 fluorines. And you might just, stop there and think, oh, it must be tetrahedral. We've got to keep going, though. We've got to look at the total number of valence electrons, and we have to look at formal charges. So what we'll ultimately end up with here is we'll end up with a lone pair on the sulfur. This Lewis structure has 0 formal charges. So we have a lone pair and 4 bonding pairs, and so that's a total of 5 electron groups. 5 electron groups make the trigonal bipyramid. In the trigonal bipyramid, the positions are not all the same. The ones around the middle, the equatorial balloons, have more space from their neighbors than the axial with the equatorial. So that lone pair is not going to go into an axial position because then it's going to have 90-degree angles with its neighbors. If it goes into an equatorial position, it has 90-degree angles with these neighbors, but 120-degree angles with these neighbors. And so that's a little more space, and so that's what it's going to do. So the lone pair needs the most space, so it'll go into the equatorial position. That's the electron geometry, is bipyramid, trigonal bipyramid. The molecular geometry, we make that lone pair invisible, and we end up with this. That's called a seesaw structure. So here I have a ball and stick model of the trigonal bipyramid. And so here's the girl spinning, and there's her tutu going around. So the lone pair is going to be in the tutu, in the equatorial position, and so I'm going to pull the atom off of that one, because this one has the most space. Now the reason it's called seesaw, you tip it over, and it's like a seesaw. Teeter, totter, bread and water, right? So it's a seesaw. What if we have two lone pairs? So here's bromine trifluoride. There's two lone pairs on the central atom and 3 bonding pairs, a total of 5 groups, again, with the trigonal bipyramid. But now we have to pull a second atom off, making a lone pair. And that lone pair also wants as much space as possible, so it's going to take one of the other equatorial positions. So we've got this. This is the electron geometry, trigonal bipyramid. 2 lone pairs here, make those invisible, and then we have the shape of a T. Well, that's called T-shaped. Xenon difluoride, Lewis structure is right here. 3 lone pairs and 2 bonding pairs. Again, 5 groups. Electron geometry is going to be a trigonal bipyramid. 3 lone pairs, though, we put those in the equatorial positions where they have the most room. So those are going to go around the middle. And then we make those invisible, and what we have left is this linear structure. So this is a little girl, and her tutu's invisible. It's okay, she's wearing a leotard. She's not naked, but her tutu's invisible, you can't see it. Any questions? Six electron groups. So here's bromine pentafluoride. We've got 6 electron groups. That makes an octahedron. So there's the octahedron. It's 6 different groups, and they're going to spread out equally. It's all 90-degree angles. So does it matter where we put the lone pair? No. All of these positions are equivalent. So we'll just take one and make that one the lone pair. So now we've got this guy. Now he's kind of lopsided. And so you make that invisible. So I'm going to even pull the bond off there, make that invisible, and then you've got this. So that's kind of looks like a faucet handle or something. Let's turn on the water. That's a square pyramid. So the base of it is a square coming up to a point. Instead of a trigonal pyramid with a triangular base, this has a square base. So it's a square pyramid. The lone pair could be anywhere. 2 lone pairs on that, such as xenon tetrafluoride. So we've got this square pyramid, and now we're going to take off another lone pair. Now it matters which one we take off, because this lone pair is very repulsive and the other lone pair is very repulsive. So they want to be as far away from each other as possible. So we're going to take off the lone pair, the atom. We're going to put the lone pair on the opposite side. So The lone pair, one is on the top, one's on the bottom. And then when we make those invisible, the molecular geometry, just looking at the atoms, and that one's square planar. All of the nuclei lie in the same plane, and it's in the shape of a square, so square planar. So here's a table in your book, which is useful. Here's number of electron groups, number of bonding groups, and number of lone pairs. The electron geometry, the molecular geometry, approximate bond angles. Here's examples, Lewis structures, and the models. You could look things up in this table, but I'm not going to give you the table on the exam. The best thing to do is what we've been doing, figuring out how many electron groups, how those would get away from each other, like that number of balloons would get away from each other, and then looking at, well, if there are lone pairs, those guys are invisible, and then describing the shape. So summary, we can figure out the geometry of a molecule based on the number of electron groups on the central atom. The number of electron groups is determined from the Lewis structure, so you got to start with the Lewis structure. This is very important. Each of these counts as one group. A double bond is one group. A triple bond is one group. A single bond is one group. A lone pair is one group. A lone electron in a radical is a single group. The geometry is determined by the repulsions between those groups. Bond angles can vary because multiple bonds are bulkier than single bonds, and lone pairs are more repulsive than any type of bond. And so that can skew it a little bit, but the geometry will be the same.